Hi, welcome to AB Video 4.4e Part 1, Total Accumulation versus Net Change. Okay, so we're going to look at this in two ways. One is looking at it from the standpoint of motion, and then we're just going to look at whatever is accumulating. So if you go back to the motion version, if you think about if an object, a car, a person travels in the same direction the entire time, which means that the velocity is either positive the whole time or negative the whole time, then the total distance that they will travel is the same as their net displacement. Okay, now what I mean by that is obviously the total distance is how far you've actually walked. So if you were wearing one of those little things that counts your steps, the distance you actually traveled. The displacement, what's called the net displacement, is when you stop, that's the distance from where you started. Okay, so if you were to travel in the same direction the whole time, so let's say this is a number line, and let's say there's a bug on this number line, but I'm showing it up here so you can, if I wrote it down here, you wouldn't see it. So this bug starts at t equals 0, the bug starts at position 4, and the bug moves to the right for the first 5 seconds, and when he stops, he's at position 11. Well, you can see in this particular case, the distance he covered was 7 units, between 4 and 11 is 7 units, but it's actually also his net displacement. Where he stops is 7 away from where he started. Okay, so in this particular case, the total distance is equal to the net displacement. Now, to get the net displacement or total distance, you're going to take where is he, what's his position at 5 seconds minus what's his position at 0 seconds, which is, of course, where you get the 7, because at 5 seconds, his position is 11 to the right of the origin, minus, and at 0 seconds, which is when he started, he was at 4 units to the right of the origin. So the total distance and net displacement in this case are the same, and they are 7. Well, how can we come up with this? Well, if you think about it, if you were to integrate the integral from 0 to 5 of the velocity of a function, you know that when you integrate the velocity, you get the position function, right? Because when you differentiate the position, you get the velocity. So when you anti-differentiate the velocity, you get the position. And if you evaluated that from 0 to 5, lo and behold, you would get s of 5 minus s of 0, which would be your 11 minus 4, which is 7. So we say that if the object travels in the same direction the whole time, the total distance will equal the net displacement. And that net displacement is always going to be the integral from the starting time to the stopping time of the velocity of the function dt. And that will give you your net displacement. And if the object is traveling in the same direction the whole time, that will also give you the total distance. Now, I want you to look at this picture over here. If the x-axis represents time and the y-axis represents velocity, then what this means is for 3 hours, this car is traveling at 50 miles an hour. He doesn't slow down or speed up. He travels at 50 miles an hour for 3 hours. Well, if you think about it, the distance he's traveled, you remember this from middle school, the distance is equal to the rate of speed times the time. So that's the velocity times the time. Well, if he's traveling at 50 miles an hour for 3 hours, then the total distance he's covered is 50 miles an hour times 3 hours, which would be 150 miles, which is the area under that curve. So what happens is the area, if you have a time velocity curve, the area under the curve between t equals 0 and t equals whatever it is going to give you actually the total distance that was covered. Okay? We're assuming right now the velocity is positive the whole time. Okay, so another way of looking at that, of course, is in this case, your dt is the width of your rectangle, and your v of t is the height of your rectangle, and that's going to give you the area of the rectangle. Now, I do want to point out that we are integrating the velocity to get the position function, but if you think about it, the velocity is the derivative of the position function. So if you look at this expression, you are anti-differentiating the derivative. Well, the antiderivative and the derivative would cancel out each other's effects, leaving you with the position, which is the distance.